With that, let me start. So I am Marisako, together with Julian Corch here, both of us at Oxford University Side Business School. We are co-organizing this series on Oxford Future Professionals. We have a thematic focus on responsible AI this year, and so this is a third in our series on the topic. So it's my pleasure, great pleasure to introduce Sayash Kapoor, who is a researcher at the Center for Information Technology Policy, Princeton University. He's been there for quite a few years now, but prior to that had worked for Facebook, both in the US and I gather in London as well, in charge of content moderation. He's a computer scientist by training, and from that perspective, he's going to tell us something about AI, which is evidence-based in various arenas, science, law, and safety. I should also say that he is a co-author of a book called AI Snake Oil, what AI can do, what AI cannot do, and how to tell the difference. And it's one of the most insightful books on AI that I've actually read in the recent past. So with that, I'm just going to say that Sayash is going to talk for about 45 to 50 minutes. It's given this format, it's always difficult to interrupt and ask questions. So if you have any comments or questions as he talks about various topics, do make use of the chat function. And at the end, we have a good chunk of time to engage him in Q&A, and we can bring some of those chat function questions into play as well. So without any further ado, over to you, Sayash. Thank you very much for making the time.
Thank you so much for having me. It's a real pleasure to be here, and I'm very excited to share some work we've been doing for the last few years on AI's impact on three different domains: science, law, and societal impact, and specifically the risks AI poses to society. So over the next sort of 45 minutes or so, I want to talk about the frameworks we've come up with for thinking through the societal impact of AI in these three fields, starting with scientific research. And when I say AI's impact on scientific research, to be a bit more specific, I'm talking about AI is used to make claims about the world. So this on the slide here describes a rough sort of thinking pattern or an intuition pump for what I mean by the term AI-based science. We have the world. We have some data that we collect from the real world, from the environments by running experiments. We use models to fit to this data. In particular, in this case, we use AI. From these models, we can make claims about models. So we can understand how these models are processing data, what relationships they find, and so on. And based on these claims about the model, we can then go back and make claims about the world. And this process of making generalizable claims about the world based on this analysis of data based on AI models is what I'm calling AI-based science. AI can also have other types of roles to play in scientific research. We'll talk about those towards the end of this discussion. But primarily, when I talk about AI-based science, AI is at the core of the process. It is really being used to make the claims about the world. It isn't being used as a tool or as an engineering artifact, but rather as the principal artifact of scientific interest. And if you look at adoption of AI across scientific fields in the last 10 years or so, we've seen this rapid uptick. We've seen this sort of hockey stick graph with adoption of AI going up across scientific disciplines, across research disciplines. And I think for lots of people, this is cause for optimism. But over the next few minutes, I want to argue that this should be extremely distressing for all of us who care about the way in which research is done and also about the quality of research. And I want to point out two main types of risks in this rapid adoption of AI. One is errors in individual studies, which is partly due to the fact that AI methods can be very tricky to adopt if you're coming from traditional statistics. And the other part is that the epistemology of these fields lags the technology significantly. And we can't basically wholesale update the epistemologies of disciplines. That requires really hard legwork, which we need to do over years or perhaps decades rather than adopting AI wholesale. So when I talk about individual studies, I basically mean an individual paper's ability to internally validate that the paper is sound. So how do we tell if an AI system that we've created to get scientific insights or for other engineering works, how do we tell if it performs well? The dominant paradigm is to use benchmark data sets. You train AI systems on one part of the data set, which is often called the training set, and then you test them on another sort of held out part, which is not touched before this evaluation. And the reason to do this is that if you expose AI systems to the data set you'll be evaluating them on, they might just memorize the patterns in the evaluation set, but not actually do well in the real world. So in other words, in the graph that in the figure that we looked at earlier, you might have claims about the model that don't accurately represent claims about the world, simply because the model has memorized what it is going to be evaluated on. And this is what could lead to exaggerated results. You might think the AI system performs more accurately than it actually does. And this process of training on the test set, or more broadly, of teaching to the test, of figuring out the patterns in the data set, but not in the real world, is called data leakage. And there are many types of leakage that we've seen arise over the years in AI-based science. Perhaps the simplest example of leakage is when there is no train test split. So in other words, let's say you have a data set that is used in its entirety to train an AI model. This is a textbook example of what's called overfitting. It's the most basic example of leakage because the AI model could basically just memorize what's in the data set. Yet we found that it is surprisingly prevalent across fields. So in particular, this review by Polrak et al. Found that of 100 papers that used AI in neuroscience, around 45 of them did not use any separate test set at all. A second example of leakage is when you train the model on a data set that has features that are not legitimate to use for the task at hand. So that's a bit of a mouthful. What I mean by that is, let's say you have a data set that contains features that you're using to predict some outcomes, but these features are themselves determined after the outcome is determined. One example of this is, let's say you're building an AI model to diagnose hypertension for new patients who come into the hospital. If the model is trained on data that includes the fact that these patients have been prescribed antihypertensive drugs already, then this model is not really telling much about how accurate it is at predicting hypertension. It is taking doctors' diagnoses of this patient's hypertension as an input. And as you can imagine, this type of model does not really have any clinical utility. But once again, this type of error seems common in AI-based science. A third and final example of data leakage is when you train the model on one distribution, but you expect it to generalize to a completely different distribution. Here's an example of that. So a paper that was trying to review many models that were developed for diagnosing COVID-19, this was by Michael Roberts and others at Cambridge, found that in many cases, papers basically used data sets where all of the images of patients with COVID-19 came from adults, but all of the images of patients without COVID-19 came from children. So instead of actually diagnosing if a patient had COVID-19, these models were simply distinguishing adults from children. Now, once again, you can imagine that distinguishing adults from children is not really what researchers were trying to do when they set out to build these models, but that is in fact what the model ended up learning. And so in each of these cases, claims about the model, claims about the accuracy of the model or its efficacy don't translate to claims about the world when you have errors in data leakage. And once we sort of realized that this was a problem that kept recurring, we tried to do some sort of systematic analysis for how often these errors occur in AI-based science. And so with my colleague and advisor, Arvind Narayanan, I sort of did this systematic review and found that there were over 250 papers across over a dozen fields that were affected by reproducibility errors because of data leakage. Perhaps more concerningly, it turned out that each of these fields was independently rediscovering this error. So it wasn't as if the errors in one field informed practices in a separate field. All of these fields were basically proceeding to find these errors somewhat independently. So this was back in 2023. In 2024, we redid this analysis and found that the number of papers that suffered from leakage in our review doubled. Across 30 different fields, we found 600 plus papers that were affected by data leakage. So to address this error and other similar errors in AI-based science, in individual studies of AI-based science, we tried to come up with a checklist to reduce the rate at which these errors occur, to inform people who are building these models, to inform reviewers of scientific research so that they can catch these models more easily, and as a resource for journals and conferences and other publication venues to spot these errors. This was inspired by this tradition of checklists within health research. So for example, the Equator Network hosts over 500 different checklists for specific tasks within health research, for specific kinds of trials, or for reporting requirements, for systematic reviews, and so on. And we came up with the reforms checklist, which does a similar job, but for AI-based science. So reforms consists of 32 questions, all of which correspond to 8 different parts of a typical machine learning or AI pipeline. And in particular, these questions are aimed to help surface instances of leakage rather than help correct them, because surfacing leakage is far easier than correcting them in our experience so far. So there is some hope that with the adoption of reforms and similar checklists, we might still be able to salvage some of the individual studies or prevent some of the sorts of errors in these individual studies. But perhaps more concerningly, some aspects or some types of risks of rapid AI adoption aren't really as easily amenable to this checklist-based approach. And that's because the epistemology of different scientific fields lags well behind the technical advances that AI is bringing to the table. One way to look at how this sort of functions in scientific research, and this is a very simplified sort of diagram, is to realize that science isn't just a collection of facts. In fact, if you look at sort of these different levels at which science operates, you have individual findings where you have specific facts about the world, and we just sort of saw how much work it takes to translate claims about models to claims about the world. But then all of these individual findings are operating under certain theories about the world. And finally, all of these theories themselves, in turn, are operating under certain specific scientific paradigms. And our claim is that when you have faster progress in one level of this scientific stack, if you will, when you're having faster progress at the level of individual findings, let's say, that does not necessarily lead to progress in better theories about the world, and in turn does not necessarily lead to new paradigms that science needs to adopt. And the fear is that this is precisely the situation we'll end up in, or we might already be in, when it comes to the adoption of AI across scientific research. So there are many examples of fields getting stuck in a rut, even when they continue to produce findings at the individual level extremely well. Alchemists, before they developed techniques like, before they came up with the models of matter, they developed the techniques vital for chemistry, like distillation or crystallization or sublimation. Geologists, before plate tectonics, had amassed a vast amount of data on many, vast amount of observational data on many sort of records on rock types, on fossils, and so on. Biology before evolution was similarly stuck in a rut where you had like this immense amount of data that was being collected, but no overarching framework or paradigm that would explain all of this. And once again, like the fear is that this might be happening in machine learning-based science or AI-based science. And to see why, you could think about AI as essentially operating under the predictive paradigm of modeling. So basically, we are trying to use AI systems basically only with observational data, and they promise to, in many cases, obviate the need for theory. But prediction does not equal explanation. And accuracy considerations alone, like the considerations that are driving the adoption of AI over older techniques like linear regression in many cases, they won't alone be enough to resolve the debate between different theories, different competing theories that all explain the facts. And one example for this is epicycles. So before the Copernican revolution, researchers had come up with many different ways to model the movement of planets. In fact, this way of predicting planets' motions was so accurate that modern planetariums still use the epicycle model in order to come up with planet trajectories. And initially, when the Copernican revolution replaced this notion, the reason it was able to do this was because of Occam's razor. The initial predictions from this model were no more accurate. In fact, they were less accurate than the predictions from epicycles. And so this is precisely what I mean by scientific progress requiring epistemological advances and not just improvements at the individual level. So automating all of science or incorporating AI methods in all of science seems to be far from where we are right now. And I think we should proceed with caution in terms of adopting AI across these scientific methods. But what about adopting AI in developing AI research? So this is a much smaller component of all of research. And this is, again, an area where there has been a lot of interest recently. Many people have claimed they can automate all AI research, but all of the current attempts that we've seen at this goal seem quite lofty and in many cases misguided. One example is Japanese startup Sakana AI, which sort of promised to create the AI scientist. They created a tool that they said would automate the end-to-end process of scientific discovery in AI research. But a few days later, when this system was actually evaluated, it turned out that there were many red flags. The system was not evaluated for novelty. It had a lot of errors in many papers that were generated. And in order to review if the papers were any good, the researchers at Sakana simply used another language model. There was no peer review process. So at Princeton, we've been trying to build benchmarks that can help us sort of do something far simpler than automating all of AI research. In particular, we created a benchmark called Core Bench, and the tasks in the benchmark are far simpler than automating all of AI research or all of science. Given a paper and the accompanying code and data, we tried to create a benchmark that would allow us to evaluate how well AI can automate reproducibility. So in other words, all an AI system needs to do is, with access to the paper's code and data, reproduce the paper's results. Now, this is, once again, I want to emphasize, a far easier task than automating all of science or all of AI research. And yet, we found that the best agents today cannot score more than 40%. And to be fair, like, even if you can automatically reproduce 40% of the papers, you could save researchers a lot of time. But to argue on this basis that we'll soon automate all of science or all of AI research using AI is extremely premature. And so we can look at sort of the tasks needed to automate AI research as some sort of a spectrum. On the far left of the spectrum are computational tools. So you can have tools like retrieval, you can have tools that help you with reproducibility. One step to the right, you have tools that can actually help you detect errors in your data analysis, perhaps run some simple scripts automatically. A third step further is idea execution. So researchers being able to sort of give AI systems ideas, perhaps in natural language, and getting initial results or hypothesis tested. And to the far right of the spectrum, you have full automation. AI systems currently struggle with the first level of this task. We do have systems that can retrieve scientific research meaningfully. We do have simple computational reproducibility tools, but both of these have a long way to go. And if we look at the spectrum towards full automation, I think we have much further to go compared to where we are right now. Okay, so this was an analysis of how scientific research can struggle to adopt AI methods. I now want to move a little bit to the legal applications of AI. And in particular, I want to cover 3 different types of legal applications. The first is applications requiring information processing, so things like summarization or translation, e-discovery, and so on. The second is tasks requiring creativity or reasoning or judgment. So these can be things like actually preparing the legal filings, assistance with research, or resolving dispute automatically. And finally, we look at AI that's used for predicting future outcomes. So these include risk predictions in criminal justice, as well as predicting the outcomes of court decisions. Let's start with information processing. So it turns out that language models like ChatGPT can be used for many types of information processing tasks. They can summarize text, translate between languages, transcribe things, and so on. But special purpose software, especially in the legal domain, has actually long been able to do similar tasks as well. For example, here's an article from the New York Times back in 2011, so almost 15 years ago, where the potential for AI in e-discovery was highlighted. What's new here, though, is that a single tool can be instructed in English to perform any of these tasks. And we do think these tools can be useful, but that's especially the case for lay people who don't have expertise in a particular domain and who have not previously used purpose-built software for information processing. But perhaps not really for the legal experts who already have the relevant expertise and already have a bunch of automated tools to help perform a lot of these tasks. And then, of course, there's a long way to go in terms of factuality. So for instance, a major issue with language models is hallucination, that is fabricated content outputted by these models. A rough intuition for why this happens is because language models generate text incrementally. So if there's an error in the first part of the text, they can keep outputting the text, taking that error for granted. And they're also trained to sound more convincing. But in their attempt to be convincing, they sometimes lose out on factuality. We'll come back to the problem of hallucination in the next section, which is on tasks that require creativity, reasoning, and judgment. So compared to information processing, this is a task where if language models were actually useful, they could have a big impact on the future of the field. And indeed, there has been a lot of hype around AI for these tasks. When GPT-4 was released by OpenAI, the company claimed that it performed as well as the 90th percentile bar exam taker. Another example is this company called US startup called Do Not Pay, which claimed to have built the world's first robot lawyer. In fact, the CEO of the company even claimed that the company would pay any lawyer or person $1 million for arguing a case in front of the Supreme Court and simply attaching an earpod and repeating what the Do Not Pay system said. But the reality is unfortunately far sadder than this hype. We've seen over a dozen cases now of lawyers falling prey to hallucinations. And we have also now, in the last few months, seen an FTC case against the company Do Not Pay for misleading customers. Now, you might think that Do Not Pay is a startup. This is what startups do. They sort of try to incentivize adoption by hyping up their products. So how have more seasoned companies fared? So much more established tech law firms like LexisNexis and Westlaw have launched generative AI products that they claimed have hallucination-free legal citations. But when Stanford researchers evaluated LexisNexis and Westlaw products, they found hallucinations in at least one of 6 queries, and in some cases, in up to a third of the cases. In some cases, hallucination basically completely reversed the intentions of a case. In others, it completely made up paragraphs. And this is an example of what 4 of these hallucinations look like with their diagnosis. There were over 200 in the examples they looked at. Now, in response to such criticisms, many AI researchers might respond by saying that hallucinations might be solved very soon. But it does seem like the challenges to hallucination have been constantly undervalued or underrated by AI researchers. And so far, we don't even have research ideas that might lead to a full reduction in hallucinations, let alone a working solution that can be deployed to products. Coming back to the question of how we evaluate legal tools, especially tools for legal reasoning, in the past, the field of AI has used benchmark evaluations. And benchmarks refer to this sort of specific set of questions as a reminder. And we've tried to import these same practices into the evaluation of AI for legal tools. But unfortunately, for the latest wave of language models, especially if you're evaluating them on professional tasks, there are many problems with this type of evaluation. The first is that language models are trained on huge amounts of data. But when you train a model on terabytes of data, it is likely that the questions that you have in any given benchmarks might already be in the data set. So this is another example of leakage, specifically known as contamination for language models. A second issue is the lack of construct validity. That is, the questions that are used in typical benchmark evaluations, such as the bar exam, don't reflect what a lawyer does in their day-to-day. For example, it's not a lawyer's job to answer bar exam questions all day. And the final problem is prompt sensitivity. So the way the questions are asked can lead to large changes in the answers. So even if a language model does well when a legal expert asks a certain question, they might not do well when a layperson asks a similar question, but in a very different language. So these are all of the sort of limitations of benchmark evaluations of AI, especially when it comes to evaluating legal tasks for creativity and judgment. And this brings us to the third type of legal application, which is prediction, both in courts for predicting criminal risk, as well as for predicting the outcomes of court decisions. So one of the most prominent examples of such a task in the last few years is this notion that we can predict which criminals should be held pre-trial and which ones should be released. Or sorry, which defendants should be held pre-trial and which ones should be released. It is really hard to predict the future, and AI doesn't change that. But unfortunately, what we've seen is this rapid proliferation of AI tools across tasks when you have to predict future risk of people. One of the most prominent examples is this ProPublica study, where I have a screenshot of this investigation from the right, when Julia Angwin and colleagues looked at bias in this tool that was used to predict which defendants are at risk of recidivism or not turning up for the court appointments. Now, what stood out to me from this investigation was not just the fact that there is a lot of bias, but actually that the accuracy of these systems is really, really low. So in this case, the system that was used was called Compass, and the accuracy of the algorithm was around 65%. Further, it turns out that the algorithm was using 137 features about a defendant, but it was no more accurate than lay people's judgment about who is more likely to recidivate or not show up for the court appointment. And in fact, a follow-up study found that a simple two-variable formula, a defendant's age and the number of priors, had a similar accuracy as the original Compass algorithm. The key thing to keep in mind, though, is that in domain after domain and study after study, we found that it's really hard to predict the future, and AI doesn't change that. But despite the low accuracy, in this case, despite the accuracy of just 64%, we are considering this accuracy good enough to make life-changing outcomes about defendants. Keep in mind that random guessing alone can get you to 50%. So this is in the field of predicting individual people's futures. What about predicting court decisions? So for instance, here on the screen, we can see an example of such a recommendation. Can AI be used to automate or predict judicial decisions? This example is from 1963. That's right. For over 60 years at this point, we've been trying to use computers to predict the outcomes of judicial decisions. So how well have we done? It turns out we haven't done very well at all. A recent paper by Medvedeva et al. Looked at this entire line of research aimed at predicting the outcomes of court decisions. And they found that in the vast majority of cases, the papers that were trying to make these predictions suffered from basic errors. One of these errors were data leakage. There were also errors when the documents that were used as an input to the model already contained the outcome of the case itself. So as you can imagine, once again, predicting the outcome of a court case based on the final opinion does not really count for much. And when researchers have tried to fix these errors and reevaluate AI, they found that, once again, AI isn't very good at predicting the outcomes of court cases. So for example, the jury model at predicting future cases and then evaluating how well it did has an accuracy of around 60%. very much like criminal risk prediction. It's not very much better than a coin flip. So as a quick recap, these were the three types of tasks where AI is being used quite heavily when it comes to legal applications. And as we go from the left to the right, we can see that the clarity that we have on the correct answer keeps reducing. For information processing, we have a lot of clarity on what the correct and incorrect answers might be. For creativity and judgment, experts might reasonably disagree. And for prediction, there are these inherent limitations to predicting the future, both because we only observe a part of the relevant data and because there is inherent uncertainty in predicting the future. So we don't expect AI to get too much better at it. So basically, as we sort of proceed from the left to the right, we think the use of AI will become harder and harder, basically impossible for some types of prediction tasks. And in order to build AI systems that work well, we first have to come up with evaluation metrics that work well for all three types of domains. And I think the places where AI systems are most useful, things like information processing, are also where we already have existing tools, whereas when we have the scope for widespread impact because of the use of AI, such as in tasks like creativity and judgment, that's why evaluation is also really hard. This brings me to the third part of my talk, which is about evaluating the societal impact of AI. In particular, I'll look at the risk of releasing AI models openly. So over the last few years, we've seen a lot of discussion and discourse around the impact of releasing extremely powerful AI models openly, that is on the open web for anyone to download. Companies like Facebook and Mistral have released AI models that are extremely capable and that can still run on individual users' laptops, perhaps. And this has led to a lot of discussion in research, where we've seen examples from people who are claiming that open models pose societal risks, including the risk of future pandemic agents, as well as research on the opposite direction, where we've seen claims that openness is necessary to ensure people's safety. We've seen discussion on open foundation models in policy, for example, in the 2023 Biden-Harris executive order, as well as in the EU AI Act. And we've seen a lot of discussion on the impacts of open models in the media. And a lot of this discussion has primarily focused on the risks of open models, because once you release an open model, revoking access to it is fundamentally impossible. Even if the company that originally hosted the model takes it down, you might have users who still continue to share the model, perhaps on peer-to-peer torrent websites. And as a result of this trepidation about the release of open models, we've seen a lot of claims about how things could go wrong. So for example, in 2023, this team from MIT claimed that openly releasing language models can basically allow rogue actors to create bioweapons. Now, if this is indeed true, then we should take this risk very seriously, right? Bioweapons can cause massive societal damage. And I think there's basically like an all hands on deck situation if open foundation models, especially those already released, could lead to this such types of attacks. On the other hand, a follow-up study from Guha et al. Critically analyzed the claims in this paper and found that browsing Wikipedia actually leads to the same information or pointers to the same information as the MIT paper for how to create the next pandemic. So these two pieces of information lead to fundamentally contradictory policy solutions. If you're looking at the impact of open foundation models, on the one hand, there are researchers claiming that they can improve or democratize access to bioweapons. On the other hand, if the same information is found on Wikipedia, then that might not be very dangerous at all. So we wanted to reconcile these two ways of looking at the risks from open foundation models. And in this work with Rishi Bomasani and others at Stanford, we came up with a risk assessment framework for analyzing open foundation models. This is largely drawn from the threat modeling framework in cybersecurity, and it goes through all of the specific steps that you need to accomplish in order to carry out some sort of societal harm or some sort of societal impact from open foundation models. It starts by asking what the levels of existing risk is and what the levels of existing defenses are. And then most importantly, it asks about the marginal risk of openly releasing a foundation model over and above the existing technology that people already have access to, things like web search on the internet, or in the context of policy discussions around curbing the releases of open models, the marginal risk compared to releasing closed models. It then goes on to the defenses against this risk and asks people who are carrying out this analysis to highlight the uncertainties and assumptions. And in the time since, we've seen many analyses of the risks from open models in which have this marginal risk notion. So for example, Rand carried out the study of AI used in large-scale biological attacks. And what they found was that biological weapon planning ability currently lies beyond the capability of frontier LLMs. And the way they did this was by comparing teams that had access to the language models and the internet versus teams that just had access to the internet. So this is precisely what I mean by the concept of marginal risk. You look at the status quo and you compare it with what happens when we add openly released foundation models to the mix. So this is for the case of bioweapons. There have also been concerns raised about cybersecurity threats. The threat is that language models are already good enough at writing code and understanding vulnerabilities in code. And so once released, open models could be used to identify and flag these vulnerabilities at a massive scale in order to exploit these vulnerabilities and get access to critical cyber infrastructure. And it is indeed true that both open and closed models can detect these cyber vulnerabilities. So on the left here is GPT-4, and on the right is Llama 2. Both of these models were prompted with, so I prompted them with like a recent bug that was found in an open source repository. And both of these models were able to diagnose the bug and offer ways to exploit it. But the catch is that it's not as if openly released AI models have any more of a societal impact compared to the closed models, simply because it's not as if closed model developers can monitor and moderate every single instance of cyber vulnerabilities that their models are being used for. And that's not because of some limitations in terms of their moderating infrastructure, but rather because finding cyber vulnerabilities is can both be used for good and for bad. So monitoring cyber vulnerabilities can be used by a defender to prevent these bugs from occurring in the systems. And it can be used by attackers to exploit existing systems. And crucially, the model that is being developed here does not really know which use case it is in. So most sort of defenses at the level of the model developer, I think, will fall flat. There's another reason to think why openly releasing language models will not lead to these sorts of negative societal consequences. That's because whenever we've come up with automated tools to uncover cyber vulnerabilities, it has largely led to improved defense. That's because attackers have access to the same tools as defenders do, and defenders can also use these tools to prevent cyber attacks. For example, for the longest time, around 30 years now, we have had access to automated cyber vulnerability detection tools that were way better than humans at finding bugs. These were called fuzz targeting systems. They could automatically work at scale and find bugs in a much greater quantity compared to humans. And yet the development of these fuzz targeting tools was primarily funded by the billion-dollar cyber defense industry as well as the government, because both of these institutions realized that better access to uncovering cyber vulnerabilities allows defenders to more quickly fix them. And we are seeing the same hold true for the use of AI in cybersecurity as well. So just as a couple of examples, Google incorporated their language models to improve the security of all of their cloud users. And there's this open source project called OSS Fuzz, which performs fuzz targeting for over 1,000 prominent open source repositories. It finds bugs in these repositories and alerts the developers. And this project has also benefited from the use of language models. They're now able to identify way more bugs and alert these developers. So both cybersecurity and biosecurity, in my opinion, are cases where the marginal risk of releasing AI models is quite low. In contrast, the marginal risk of releasing AI openly for things like non-consensual deepfakes is quite high. We've already seen widespread use of text-to-image models for creating non-consensual images, especially a phenomenon in schools and for teenagers. And all of the defenses that we might have fall flat, especially in the face of encrypted applications like Telegram. Still, we have seen some efforts being made to prevent the spread of non-consensual deepfakes. For example, we've seen legislation both in the US and in the UK, specifically targeting the creators and distributors of such deepfakes. We've also seen how we can come up with platform-level interventions. So, for example, platforms have now started to already store hashes, cryptographic hashes of known non-consensual deepfakes, and prevent such content from being posted to their platforms in the first place. There are also efforts like Take It Down, which is created by the National Center for Missing and Exploited Children, which does the same for non-consensual deepfakes of children. Okay, so this brings me to the end of my talk, and I wanted to highlight a few key takeaways. The first is that across the three case studies in science, in the law, and in evaluating the societal impact, good evaluation is a key bottleneck to understanding the societal impact of AI. Whether it is in understanding how well AI can be used for science or the law, or even in understanding what the real risks of AI are, we don't really have the level of evaluation that we might want. A second is that for both scientific and legal research, one of the areas where I see AI genuinely being helpful is in automating routine tasks that speed up scientific and legal research. So for scientific research, this is like the development of computational reproducibility tools and retrieval tools and so on. For legal research, this might be information processing. But this doesn't automatically imply that full automation is around the corner. In fact, I think it does quite the opposite. It sort of, the use of AI in scientific research should sort of be a cautionary example in the adoption of AI, especially because we've seen widespread errors in the fields that have already adopted them. On the flip side, if we move from the benefits to the risks, even when you're understanding the risks of AI, it is really important to focus on the marginal or the incremental risks that AI poses over and above existing technologies. So in other words, framing something as an AI-enabled problem when it is also something you can do using web search, I think is a fundamental flaw in many of the arguments about AI risks today. And finally, I think domain experts have a big role to play, both in developing better evaluations and in understanding the benefits of and risks of AI within the specific fields. In scientific research as well as legal research, we've seen some of the best examples of rebutting hypes and understanding the improvements critically has come from legal scholars as well as scientific experts within those fields themselves. And I think this will continue to be the case for the time to come. All right, with that, maybe we can switch to Q&A. Thank you so much.
Great, thank you so much,